Welcome back. In the last part of this lecture, we'll be talking about other ways to solve equations that involve some factoring perhaps, or some other clever transformations of the original equation. Some things to keep in mind, of course, would be that if we ever square both sides of our equation or raise both sides to an even power, then potentially there are extraneous solutions that you've created, which means you'll need to check your solutions. Also, we'll need to think about things like if we multiply both sides of the equation by something that's potentially equal to zero, you could potentially have created an extraneous solution there. Again, another time where you'd need to check your solutions. Of course, in addition to that, we also have other things that we know, which would be that if you had a rational expression, any value of x that makes the denominator 0, that would be an excluded value. That would be something that couldn't be a solution for the original equation. And also, anytime we've got square roots, for this course, we're imagining that these square roots are real valued square roots only. We're only interested in roots where the inside is 0 or larger. So we're not going to be interested in things like square roots of -2, for example. So if that emerges as part of your solution, then that's not something that we'll want. So, taking a look at this first problem, we want to find all the real solutions for this equation. And looking at it, I'm going to start off first by, as usual, moving everybody from one side to the other so that I have all of my x terms and constant terms on one side, and so that I have only 0 on the other. Now, this is not a very nice looking polynomial here, but it's not terrible, because you might have noticed that there are, for this polynomial, 6 terms, which means that we have factoring by grouping as a possibility. And in fact, there's 2 different ways factoring by grouping might work. We could either have it as 3 groups of 2, or we could have it as 2 groups of 3. And I don't know which will work, if any of them, so I'll start out with what if I were to imagine factoring them as 3 groups of 2. Remember that for factoring by grouping to work, what's left behind would need to be the same for all of my groups. So in the first group, x to the 5 plus 5x to the 4, I'm able to factor out x to the 4, and that leaves x plus 5 left behind. And if I'm looking at that second group, if I'm trying to get x plus 5 left behind, there's nothing that I can factor out of 6x cubed minus 8x squared that would give me x plus 5. I could try all the possible common factors that there are, but unfortunately I'm not going to get an x plus 5. So for example, I could factor out 2x squared, but that'll leave you with 3x minus 4, and those of course are not the same thing. So that means that this approach to factoring by grouping does not seem to be working for us. So let's try, instead of 2 groups of 3, or sorry, 3 groups of 2, let's try 2 groups of 3. And let's see if factoring by grouping there works. For the first 3 terms, I could factor out x cubed, leaving x squared plus 5x plus 6. And in the last 3 terms, if I factor out -8, you'll see I'm also left with x squared plus 5x plus 6. So this factors as x squared plus 5x plus 6 multiplied by the x cubed that's left over minus the 8 that's left over. And then both of these factor relatively nicely. X squared plus x to the 5 plus 6, that's x plus 2 times x plus 3. And x cubed minus 8, you might recognize that as a difference of cubes. This is x that's been cubed and 2 that's been cubed. So using my difference of cubes formula, I would have x minus 2, x squared, plus 2 times x, plus 2 squared. And you might recall from before when I had mentioned the difference of cubes formula that the quadratic part that's left behind Usually, at most, you'll be able to factor out a common factor, but that'll be about it. Typically, this won't factor any further. And in fact, if you wanted to check the discriminant for this quadratic, b squared minus 4ac, you'd find that the discriminant is negative 12. Not only does that not factor, we're not going to get any solutions from that quadratic. So that means that for our solutions, the only ones we'll have will be is negative 2, negative 3, and positive 2. And that quadratic does not give us any real solutions. So my solution set, negative 2, negative 3, and positive 2. All right, next one up. You might notice this is a radical equation, so we could solve this by squaring both sides of the equation. That's one thing that we could do. I could isolate a radical, square both sides, then clean things up. Or instead, I might notice that I could simplify this equation if I were to multiply everybody on the left side and on the right side by square root of x minus 3. That's that technique that we saw before, that if you have a rational expression somewhere, that you could multiply everybody, left side and right side of the equation, by whatever the common denominator would be of all of your rational expressions, with the goal that it would get you to no longer have any fractions. That the root of x minus 3 and the root of x minus 3 would cancel. And actually it does something nice for the second term as well, because root of x minus 3 times root of x minus 3 is just x minus 3. And on the right side of the equation we'll just have 0. So kind of nice in a sense that with a little bit of a transformation, we've now turned this into something that's a quadratic. Now, before I get into solving, one thing that I want to think about, of course, would be we've transformed the equation. Is it possible that we are gaining solutions that don't satisfy the original equation? And so there's two things to keep in mind here, which is that number one, in the original equation, you had a fraction, and the denominator would be 0 if that square root were equal to 0, and that would happen if x was 3. So number one, we know that x cannot be 3, because that would make that first term undefined. The other thing that we know is that for these square roots, like we said before, we want them to be real value square roots only. We're imagining that what's inside those square roots does not make it square root of a negative. And so if you want root of something to be root of a not negative number, in other words, if we want x minus 3 to be not negative, then you need x to be at least 3. So in other words, x needs to be greater than 3, otherwise what's inside your square root will either be 0, which is a problem, it'll make your denominator 0 for that one fraction, or it'll be making your inside of your root negative, in other words, not a real number. And I'm going to keep that in mind here because, as you'll see, when we solve the quadratic that we have, it factors really nicely, and we come up with two solutions. But both of those solutions are values of x that make your original equation have square roots of negatives inside of it. This would give you something where your square root is not real valued. It's a complex valued square root. And if we're imagining that we're only dealing with real values only, then we would have to reject both of those solutions. So for this, if we're imagining these square roots are real values only, then there would be no solutions to this equation. If you were taking a later on math class, a subsequent one where you talk about complex numbers, and if you were allowing your square roots to take on complex values, then you could have 1 and 2 both being solutions to the original equation. But if we're, again, assuming that these roots are real values only, then 1 or 2 would make the inside of your root negative, which would make it not a real number. Okay, so we've got ourselves a rational equation to solve, and we did something similar to this in 1.1. And so I'll do kind of the same approach here, where I'll say, well, you've got a rational expression plus a rational expression equal to another one. I'll start by factoring out the denominator that's on the far right. X squared minus x minus 2 factors as x minus 2, x plus 1. And if I'm thinking about the common denominator for these three fractions, the common denominator would be x plus 1 times x minus 2. And if I multiplied all three terms by that common denominator, in the first term, x over x plus 1, the x plus 1's would cancel, leaving just the x minus 2 behind. In the second term, the x minus 2's would cancel, leaving just the x plus 1 behind. And on the right side, the x plus 1 and the x minus 2 would cancel, leaving just the numerator, just the 9, behind. Now, one thing, of course, that we need to keep in mind when we've transformed our equation, did we transform it in a way that potentially is creating extraneous solutions? And the answer is yes, we might have. We've multiplied the equation by something that's potentially equal to 0. So that means that we have potentially created extraneous solutions. So if we go back and look at the original equation, we can see that there are two excluded values. And the excluded values are 2, x can't be 2, and also x can't be negative 1. Either of those values would make one or more of the expressions undefined. So if those show up as solutions, that means we'll need to reject them. So now we'll continue on expanding and simplifying. And so we've got x squared plus x minus 6 is equal to 0. And we can solve by factoring. And we have x being negative 3 and x being positive 2. And this is where we go back and remind ourselves that 2 was one of our excluded values, so that means that we'll need to reject that solution. It's excluded. So the only solution for the original equation would be negative 3. Okay, let's do one little last bit of solving here. We've got one more problem. One is a fourth root involved here. So this is a radical equation, and we know what to do for that. I would start off with taking the left side and the right side of the equation and raising it to the power of 4. The reason we're raising it to the power of 4 is because that's what would undo a fourth root. Now, that means that on the right side, we'll now just have 5x squared minus 4. This would be the warning sign that is coming up. We raised both sides of the equation to an even power. That means that we're going to need to check our solutions. So at the very end of it all, we'll need to find out whether the value that we found for x will solve the original equation. So we'll keep that in mind, that we'll solve, but later on we'll need to go back and check those solutions. Now, as far as the solving goes, if we were to bring all of our terms to one side, you could see that this is something where it's quadratic in form. You have x squared and x to the 4, which is the same thing as x squared that's been squared. So if we were to let u be x squared, then that means u squared would be x squared squared, or x to the power of 4. So we would have u squared minus 5u plus 4 is equal to 0. And that means we would have u minus 4, u minus 1 is equal to 0. So u is equal to 4, or u is equal to 1. And that means that x squared is equal to 4, or x squared is equal to 1. And that means we're going to get 4 possible solutions in total. If x squared is 4, then x is plus or minus the square root of 4. If x squared is 1, then x is plus or minus the square root of 1. So there's 4 values of x potentially. We have x could be 1, -1, 2, or -2. And we'll have to check all of those solutions in the original equation. So now that's what we'll do next, to see what do we have for this original equation, what do we have for the left side and the right side. So I'll start with checking x being positive 1. So on the left side of our equation, that would just be 1. And on the right side of our equation, that would be the 4th root of 5 times 1 squared minus 4. Which, if you were to run this through, 5 times 1 squared, that's 5. 5 minus 4 is 1. And the 4th root of 1 is just 1. So that means that left side and right side are equal to each other. 1 is a solution. And I'll do the same thing with 2, and then I'll do -1 and -2. So putting in 2 onto the left side gives you 2. Putting 2 onto the right side gives you the 4th root of 5 times 2 squared minus 4. That's 5 times 2 squared minus 4 is 16, and the 4th root of 16 is 2. So both of those so far are solutions, yay. Let's check -1 and -2. So the left side would be -1, and the right side would be 4th root of 5 times -1 squared minus 4. Which, if you were to evaluate that, 5 times -1 squared is 5. 5 minus 4 is 1. 4th root of 1 is 1. So we have left side and right side not equal to each other. That means that we're going to reject x being -1. And we'll see the same thing happens for x being -2. If you were to put 2 negative into the left side, it would be -2. If we were to put -2 into the right side of the equation, you would have again 4th root of 16, which is +2. So again, left side and right side would not be equal to each other. So we would reject x being -2. So we found 4 possible values for x, but only 2 of them are solutions for the original equation, and that's +1 and +2.